Welcome back to our engineering mechanics lecture series, for which we are looking at everything related to forces so far. And particularly, we are still analyzing the equilibrium of particles in 2D systems, because in our next lecture we want to move on to 3D systems. But before we do that, we need to have a solid understanding of how these forces work, particularly the tensile forces, because only tensile forces act in cable structures. We talked about this a little bit last time, but today we're going to solidify that knowledge because it's so important when we move on to 3D systems. Because sometimes cable structures actually stretch a lot, we need to understand how to calculate that and how to determine the stretch in those systems. And that is often described idealistically by springs. And so one big goal of today's lecture is actually to look at springs. In fact, that's the only part that we're going to talk about theoretically, and the rest we do all in applications through solving problems. So very little theory today, only problem solving. So that at the end, which is our ultimate goal, we can calculate the tensile forces in more complex cable structures. That include springs, and then also we're going to use the educational opportunity to make our systems a little bit more advanced. So without further ado, let's move on to springs, and let's start talking about what is actually called linear elastic springs. So let's talk about those two terms real quick. So because we're only talking about linear elastic springs, so let's talk about linear before we talk about elastic. So linear in a sense means the more of something comma, the more of something else, or sometimes less, the more of something else. So of something else. And of course, this could also be less here. And this is not completely true yet linear, but in a general concept, it is true. So if we apply, let's say, more force, we get more stretch. But linear doesn't just mean more and more. It also means that if you add twice more, you also get twice more of the other thing. So it's pretty much a linear function, if you will. So let's visualize that. So of course we remember this from our basic math class. What is linear? If we have a graph, and let's say on the graph here we put what engineers call delta, which is usually displacement. And then we put a force here. So we apply a force to a spring, and then I would apply, let's say, 1 Newton, and it stretches by, let's say, 1 meter. And then I apply 2 newtons, it stretches by 2 meters, and so on. So what we would end up with would be a linear line, right? So that would be linear. Now, that is the first term, and I will come back to that in just a second, although it's a very basic, probably already understood concept. But for completeness reason, let's also talk about elasticity, or what is elastic. So elastic means that you always go back to your original shape, right? So you stretch something, and when you let the force go, it goes back to state zero. So that means it is recovering deformation after force has been removed in case of springs. So let's draw these two aspects, linear and elastic, for actually springs. So let's say I have a ceiling which is very long, so I can apply multiple springs to it. And let's say I have my very first spring here, and there's nothing on it. And I'm gonna call this length that the spring currently has, I'm gonna call that L nut. Right, so the initial length. So this is L nut. And now I'm gonna take the very same spring, but I will apply a force to it. And I will apply, let's say, 1 Newton to keep it easy for us here. And therefore my spring just became a little bit longer. And the way it got longer is really described by the difference from the initial length to the second length. So this would still be L nut, but this here is delta L. And I'm going to call this delta L1 because here I have, let's say, 1 Newton. Now, if I apply more force to the system, the stretch spring will be even longer. And so I end up with a system that is longer. And of course, I need my weight down here again. And let's call that 2 Newton. And to no surprise, I now have a different length. And that different length now is up here still L nut. And here I have delta L2. And just for completeness reasons, let's draw one more. Let's draw one that goes all the way down here. And now I have a box with, let's say, 3 Newton on it. And my stretch now, of course, is even longer. And I still have this L naught, but now I have delta L3. And in this case, delta L1 is equal to 1/2 delta L2, for example, right? So this here is twice as much as this one because I have twice as much force hanging on it. And that's really what the linearity stands for. Likewise, let's say my delta L1 is also equal to 1/3 of delta L3. Or you might as well say it the other way around. You may say that delta L3 is equal to 3 times delta L1. And so you understand now that the linear elasticity means the more force you put on it, the more it stretches, and the stretch is proportional every time you add more to the system. And that is really what this picture here signifies for you. Now, again, if let's say you call these state 1, or this is called 0, this is 1, and then second and third state, and let's do a fourth state and maybe even a fifth state. So if I now remove the force again, and I will actually draw my initial line, now I'm back to delta 0 or L nut if I removed all the force, right? So this is L nut again. And that is because it's elastic. So the jump from here to here to here, that means it's elastic. I removed this force and it restores its initial length. That is elasticity. And that is a concept that you see a lot in engineering when it comes to the elastic modulus of some materials. So it's very important that you really understand this graph and what it really means in the physical world, because so many materials are actually linear elastic, and that is one reason why we talk about this topic today. But we can talk more a little bit about springs here, and we can define springs properly. We need to add one last state here to have the complete picture. So let me extend the line here. So let's say we have another state, which is my state number 5. And now I'm actually applying a force in the opposite direction. So that now I have a force of, let's say, 1 Newton here. And now, of course, I compressed my spring. And so my L naught would still be the original length, L naught, but now I have a negative delta L, which would be this here. And so this is negative delta L, and let's call that 5. And because the spring is linear elastic, if that is 1 Newton, then this stretch delta L1 would be equal to the negative delta L5. So they stretch in the same direction. And that is really the definition of a linear elastic spring. Just for comparison, let me go back up here and let me show you what would happen if you would have a nonlinear elastic spring. So I'm going to draw this graph again. And that is something we don't deal with in this class, but I want you to understand this. So let's say you have a regular material, let's say steel, for example. Steel is initially elastic, you can pull on it and it goes back to its original length and so on. But once you go beyond a certain delta L, like once you put a lot force on it, so that it stretches too much, so you can also say that you have a delta force on there. So once you have too much force on there, you go beyond this point, then the material actually starts to become plastic and it really looks like this. Again, this is beyond the purpose of this course, but now if you remove the force, the material would actually go back to this stage. And that is something that we have all experienced before. So actually both of them, we have experienced this and this. If you take, for example, the pen and you open it up that you're using right now, there's usually a spring inside. And you can pull on it and it goes back to its original length. But once you pull too much on it, and I encourage you to do that, just find a cheap pen in your home and pull on it and pull so hard that it does not go back to its initial length. So you will actually find a behavior that is similar to this one. And that is really what is the plastic region. So again, not the topic of this course, but it's always good to know. So this is plastic. Whereas this part here is the elastic region. So that is pretty much the difference. And of course, in this class, we only deal with materials that act in this region. And this is for classes like strengths of materials and other things. We do not worry about this here. But it is important for us to understand the difference so that we can now move on to the definition that engineers use for these springs. And the first thing we need to understand is that everything that stretches a spring is considered positive. And that's easy to remember, right? So if you add some weight to it, you add length to it, and therefore you use the positive sign. So a stretched spring, is positive. And on the contrary, of course, a contracted spring is negative. So engineers automatically know when they see a positive or a negative what is acting or what is happening in the spring. So is it stretched, is it extended, or is it contracted? Like here, for example. So please keep that in mind. In fact, let's say that this is positive, this is negative. So here I have a negative, but here I have a positive, here I have a positive, and here I have a positive. That is how engineers define that. And I think now we have a solid understanding of that. Of course, we need to talk about something that you already talked about in your physics class, and that is the spring constant. And we all remember like one formula or the other, which comes from Hooke's law. By the way, Hooke's law is visualized here effectively, but Hooke's law really says that the force is proportional to the extension of the spring. So force in spring is proportional to the extension in spring. Let's highlight that. That is fairly important. because that is Hooke's law. And again, you probably already knew this from your physics class. There's no question about it. But again, we all want to be on the same page and want to have a solid understanding of the concepts that we're using in this class. So how is this formulated? And that is something you have, of course, worked with as well before. You have seen the formula in one way or the other, but let's say the force in the spring is usually equal to what is called K times, and I think in physics most students use X, but here in this class we're using S. And so this is really the spring constant. Whereas this is the stretch. And so now you of course know that this here is the force in spring. So now if you understand the relationship and the picture that we just drew above, then you will never struggle with any formulas or with any units here. In fact, look at this, right? So you know the stretch. The stretch we know is always given in what? In like a distance. Let's make it in the SI system. So let's say it's in meters. And the force in the SI system is always given in, let's say, Newton. So now you may ask yourself, what is the spring constant? And the spring constant, of course, has to complement this. So how do I get from meter to Newton? By something called Newton per meter, right? So here I need Newton per meter. And that is really how that is defined. So the real formula then reads F in Newton is equal to K in Newton per meter multiplied by S in meters. And likewise, you often need to find actually the stretch rather than the force in the spring. So when that is the case, then you have to find the stretch in meters. And that, of course, is just rearranging of this formula, the force in Newton divided by K, the spring constant in Newton per meter. So that, once again, is an important formula. So let's highlight it. This is what you need to memorize to solve the upcoming problems and therefore the problems on your homework and, of course, quizzes and exams. So please memorize this. Of course, you know this. What's important to me here is actually the physical understanding and how I derived the K value. So I know I have a spring, I know I have a stretch, and what is the unit? Because in my experience, students often forget the unit of the spring constant, and you can really derive this from Hooke's law and the definition of all the other two components, the stretch and the force. So we understand how that is defined. Let's highlight our spring constant here so that we don't forget that K is actually the spring constant. And because K is so important for our upcoming problems, let's write down one last thing. So that relates to the spring constant. Let's say you have a 100 Newton per meter spring constant K. So the question is, what does that mean physically? So please understand that if you have a spring that, let's say, initially looks like this, and then you apply 100 Newton to it. So let's say here I now have 100 Newton. Then I have a delta L of 1 meter. So in other words, what this means is that 100 newtons are necessary to stretch the spring 1 meter. So this would be a very weak spring. It would be very useless in construction or for structural engineers, but the concept applies, right? So whatever number you have, that's how much it takes to stretch it by 1 meter. And that is the real physical interpretation of the spring constant. So in real life, you will find more something like a meganewton per meter or something like that, or even larger numbers. So that then would take 1 meganewton to stretch the spring by 1 meter. But this is how you read the spring constant. And that is important to understand for engineers. Often in the classroom at this point, I ask the students to go ahead and Google the spring constant of a general sports car. so that they can calculate how much the car displaces downward if a student steps into the car. So maybe go ahead and measure your own weight and then assume a sports car spring constant. You can find that on Google. And then step into the car virtually and tell me how much the car displays downwards, right? So if I were to draw this down here, so let's say I have a car that is somewhat like that. Again, my fantastic artist skills here, but here I have a car and I know a spring constant. So there's a spring constant K, sports car. And then there is, of course, a student. So here's F student. And you can just use your own weight for this. And this you can Google. And then ask yourself, hey, what happens if the student steps into the car? And how much does the car displace? Because once the student is in the car, then you probably end up with the entire frame a little bit lower. So that would look something like this, right? And so my question to the student then is, hey, what is this delta L is usually what we call it. And so the question is, what is that value in, let's say, meters or in foot? Either one would work. And please understand that this is a car and not a unicycle. And that's all I can tell you at this point. So please be careful. Don't fall into any traps here when you solve problems like that. But you are an engineering student, so of course you got this. So let's take a look at this entire page here now. That concludes our understanding of springs. We definitely understand what linearity is now and what a linear elastic spring is. So it goes back here. We applied this to Hooke's law, and we even derived the spring constant. By the way, K stands for Konstante, which is a German word because Hooke spoke German. So therefore it's the spring constant K that defines the displacement of a spring. However, I believe we are now ready to tackle problems with springs in them. And of course, we will now apply this concept and specifically this formula to our cable structures so that we can calculate the extension or the stretch of those springs. Of course, I didn't show you how to do that here in theory, but this is easier to be shown in a practical problem. So let's move on to our example problems. So here we see our very first problem that includes a spring in a cable structure. And it is my experience that students first fear springs and they don't know how to calculate it. But as I will show you now in this application of this problem, springs are actually just an addition to what you know already. So nothing changes. You don't have to change your approach. You don't have to learn something new, except you have to add at the end what we just talked about, and that is the spring constant. And I will explain that as we move through the problem. But what we have here is a lamp of 5 kilograms that is hanging downwards, and there's one sloped member or one sloped cable and one horizontal. Think of it as a cable, but it's of course a spring. And we have node A, B, and C. And to solve this problem, just like before, we need to first release node A, because we have one known force, which is the 5 kilogram, and then we have the unknown force in cable AC and the unknown force in spring AB. And let's recall that we can really cut the system however we want to. So for example, I could release the system like this if I want to release node A, but I could also, for example, release the system like this. It does not really matter, right? So I will now draw the free body diagram for the system. I usually prefer this one, the inner one, the smaller one, but it doesn't really matter. So let's go ahead and do that. Let me pull out my ruler here and copy the 30-degree line. So first I start with my free body diagram, and my free body diagram has a cable that is sloped. It has a horizontal cable, and a vertical cable. And of course I need a coordinate system, so in this case I'm actually going to place it at the center just to do it a little bit different like I did before, just so you see that there's a variety of ways of doing this. So there's XY, and now I need to include the information that I have. First of all, I know that there's 5 kilograms hanging here, and 5 kilograms, because we're using 10 meter per second square for gravity, really relates to 50 Newton. So we're going to use 50 Newton to solve this problem. And by the way, sometimes I see students solving forces in cable structures in terms of kilograms, but that is not a force. Kilogram is a unit of mass, and if you want to solve for a force, it has to be in force units. So please keep that in mind. Now, let's move on to our unknowns. So I first have an unknown here, which is called FAB. And I have a second unknown, FAC. And understand, please, that FAB is really the force that's acting on the spring, but notice that I did this cut here, and so therefore I don't have to worry about the fact that there's actually a spring here. Even if I cut here, I don't have to really include it because the spring is not really cut. So we will only worry about the spring at the very end. All right. Of course, I need my components. There's only one sloped member here, so only that has actually components. So let's add those. And I, of course, need also directions and names for those. Remember all the rules that we have. So FACX and FACY. Last but not least, I need my angle, which is right here. Let's call that alpha, or actually that's 30 degrees. And now I can start solving. In fact, I'm going to take a very shortcut now because you're already so familiar with solving these problems thanks to all the homework that you are allowed to do in this class. So only this force can really balance this force. There is nothing in FAB that really can hold the lamp up. So the only thing that holds the lamp up is FACY. So without writing down a real equation, I already know that that is 50 newtons, right? So for your educational experience, of course, I'm going to say that you would write sum of the forces in the y direction is equal to 0, upwards positive, and then you would state that 0 is equal to plus FACY minus 5 Newton. And again, if I were in an exam, unless I'm specifically asked to write down this equation, and most often you will be asked, but if I'm not in an exam, I would have just stated that FACY is equal to 50 Newton. Let's fix that. So 50 Newton. Now, if I know that, I know everything else already, right? So now that I know this one, I can, of course, use my 30 degrees to find the hypotenuse. I can find the horizontal, and once I know that, I can actually find FAB. So let's go through that. So FACY is nothing else than FAC multiplied by the sine of 30 degrees. So therefore, FAC is equal to FACY divided by sine 30. But keep in mind that sine 30 is nothing else than 0.5, and so therefore your FAC would be equal to 50 Newton divided by 0.5, which is nothing else than 100 Newton. And that does not get any easier. This is not a result in this case because the problem doesn't ask for that. If the problem was asking for the solution to all the cables, I would double underline this right now, but here we only asked for the stretch. So to get the stretch, I really need to understand how much force is acting in this cable here, FAB. We have calculated FAC, so that's the force in this diagonal component. And what I need now is the horizontal component so that I can balance that in the x direction. So let's write down that. So if I want to find my FACX, then I really need to say that FAC times cosine 30 is that component. And so that relates to 100 Newton multiplied by cosine 30. And that is nothing else than 86.6 Newton. And so now what I know is that 86.6 newtons is actually acting in the horizontal direction here at AC. And that has to balance FAB, which now, of course, as an engineer in the real world, I would have already answered this, but for the educational experience, I would write the sum of the forces in the x direction is equal to 0, positive to the right. And 0 is really equal to minus FACX plus FAB, and that would be equal to minus 86.6 Newton plus FAB, and therefore we know that FAB is really equal to 86.6 Newton. And notice that this is technically plus, and that means that the cable is in tension, right? So understand, please, that we assumed every force to pull away from this node. Remember that this is node A, right? Let me highlight that. So this is node A. And that node A, we assumed every force pulling away from it. And if they come out to be positive, that means that we have tension. That is kind of the definition of tension here, because we're pulling away from the node. All right, but we are asked to find the stretch in the spring, and the stretch in the spring now, we can actually draw a second free body diagram for that. So to be complete here, so let's say for node A, I'm now going to draw a free body diagram for the spring. So free body diagram for spring. And that is as simple free body diagram as it ever will get. So I release the spring and I just have a force here and a force here. And notice that I need forces on both sides. So I release the spring. So really what I did here, let me go back and let me show that to you, is I cut the system like this. And only if I have arrow to the left and to the right, this can be in equilibrium. But now I have to say that the force that keeps it in equilibrium is FAB, which is equal to 86.6 Newton. And that is literally everything I need. And my spring constant equation, of course. Remember that F is equal to K times S. And so my S is equal to F over K. And applied to this problem, what that means is that the stretch in the spring is equal to the force 86.6 Newton divided by, what was our spring constant? 300 Newton. So 300 Newton per meter, actually. And if I calculate that out, what I will find is that the stretch in the spring is really 0.2857. 0.2857 meters. And this now is a real result, because that is what the problem asks of us. And so I need my answer arrow. And I now solved the spring constant problem, which hopefully learning by doing here applies, and we can now see that we only needed to worry about the spring constant once we found the force in the spring, right? So please understand that here, this cut down for the spring that I just added is equivalent to the cut up here. And so that cut is in balance. So whatever happens here to the right has to happen here to the left. So this here is actually also FAB. Maybe I should add that as well. So FAB. And once I knew the force in that spring, I just applied it to the spring, and then I calculated the stretch in the system. And it's literally as simple as that. So really what you need to learn is how to find equilibrium at nodes. So let's make that a little bit more complicated and take a look at more advanced examples. All right, our problems become a little bit more interesting now. We are now looking at a problem where we have a box hanging on two cables that are both under an angle. In fact, they are described by their relations here, 3, 4, 5 for this one, and this here is 3, 3, and then of course square root of 3 squared plus 3 squared. But we have a box here, and we assume that the dimensions that we see here are the unstretched, unloaded system. And that the box here really can only move downwards in a perfectly straight line. This may not be true in real life because the length here is different than here, and maybe the stiffness is different here. So the stiffness, by stiffness I mean the spring constant. Therefore, it may shift a little bit to the left and to the right, but that is irrelevant to us here. We move downwards in a perfectly straight line. And then we also assume that the box has a volume of 8 liters. And of course, let's write that down right away. So 8 liters of water is nothing else than 8 kilograms, and that means it's 80 Newton, right? So we have 80 newtons acting here. And now we can calculate the stretch in cable AB and AC. So AB is here and AC is here under the assumption that the box is completely filled with water. So that I already did here. The strategy to success is always a free body diagram first, and let's talk about an important aspect of free body diagrams for released systems. So I just released this system here, and what did I do? I really cut through 1, 2, and 3 parts of the structure. But in reality, I only cut through 2 unknowns. So this is not known and this is not known. This is effectively known because I have this value available here to me. Please understand that the only reason I will be able to solve this is because I have only 2 unknowns. And why is that important to understand? Because we have the sum of the forces in x is equal to 0, and we have the sum of the forces in y is equal to 0. And that means I have 2 equilibrium conditions. And therefore, I can only solve 2 unknowns at a time, because if I have 2 equations, I cannot solve more than 2 unknowns. Or likewise, if I had 3 unknowns, I could not solve that with 2 conditions. And that is why when you draw free body diagrams and when you cut the system, you always have to make sure that you only cut through 2 unknowns. In other words, if there was another spring or another cable, let's say here, let's say I have another spring here, then this would not work because I also cut the spring here, and I would end up with 1, 2, 3 unknowns, and therefore my 2 conditions would not be enough anymore. And you could say, what is with the sum of the forces in the z direction? Then I have a third condition. And I would say, yeah, that is true if you have the sum of the forces in the z direction, but it doesn't help you because this system only exists in xy. So this would not be solvable with the methods that we have in this class. Therefore, let's remove what I just drew here, and let's fix our structure and understand that we can only solve this because we are cutting through 2 unknowns here. All right, let's draw the free body diagram for node A. So free body diagram for node A. And I'm going to copy my slopes here. So the first one is a 3, 4, 5 triangle, and then we have the, sorry, that's actually a 3, 3, so that's a 45 degree. And then here we have a 3, 4, 5 triangle. And I believe we said that we have 80 Newton acting on the system. Now my unknown here would be FAB. And I have an unknown here, which is FAC. And I need components. So let's add those components. And vertical components. So F, A, B, Y, F, A, B, X, F, A, C, X, and F, A, C, Y. Now I can either use angles or relationships. So let me actually use relationships for the right side because I know that is 3, 4, 5, right? So I have 3, 4, and 5 here. But then on the other side, let's just make our life easy and let's say that I use 45 degrees. So 45 degrees. I could have, of course, also calculated the length of the diagonal, but that doesn't matter here in this case, which route I'm going down. So now we can solve this, and it's a little bit more complicated than before when we talked about the lamp. Remember, the lamp, we only had on the left side a sloped member, whereas the right side didn't have one. So now, in this case, because both sides are sloped, that means that the vertical force is shared between FBY and FACY. So that equation would read plus FABY plus FACY minus 80. Whereas the x direction is similar to what we've seen before. But in this case, let's write down the x direction first. So the sum of the forces in x is equal to 0, positive to the right, and 0 is equal to plus FABX minus FACX. And similarly, in the y direction, I have 0 being equal to plus FABY plus FACY minus 80 Newton. And once again, this is very similar to what we talked about before. I cannot solve this equation set as it is right now because I have 4 unknowns. FABX is different from FABY. But I can express, of course, FABX in terms of FAB, and I can express FABY also in terms of FAB. So let's go ahead and do that. So plus FAB, and now divide it by 5 and multiply it by, this is the x direction, so 4. So 4 over 5 minus FAC times the cosine of 45. Or actually the square root of 2, right? It's a 45-degree angle, so you could also divide it by the square root of 2, but let's not do that. Let's use the sine and cosine. So multiplied by, this is the x direction, so I prefer to use cosine. Of course, it's the same for 45 degrees angles, but that doesn't make a difference. I want to stay consistent. In the y direction, now we have FAB multiplied by 3 over 5 plus FAC times the sine of 45 minus 80 Newton. And that now can be solved because now we have 2 equations, 1 and 2, with 2 unknowns. In fact, for educational purposes, let's highlight them. So these are identical to one another, and now we can highlight them, or we can memorize that this is equation 1 and this is equation 2, which now I can solve by substitution method, which I don't believe I have to show you once again. I will just give you the results. I will tell you that FAB in this case comes out to be 57.14 Newton. And FAC really turns out to be 64.65. Once again, these are not results, although it seems that way. But what we're really asked for here is the spring stretch. So let's calculate the stretch in the springs, which FAB, the force that sits in the spring FAB. And that had a spring constant of 300 newtons. So remember once again that S is equal to F over K. And so if I do the stretch in spring, what is it called? AB. In AB, then I would take the force FAB, so that was 57.14 Newton, divided by 300 Newton per meter. And I would find that that is equal to 0.190 meters, really. That is actually a result, so therefore I'm double underlining it. And not just double underline it, I also give it an answer arrow. So now that is taken care of, but I have to do the same thing for SAC, which is the other force now, which is 64.65 Newton. But be careful now, it's a different spring constant. So let's zoom out and let's take a look at the entire picture here. So that needs to be divided by 200 newtons per meter. And if I type that into my calculator, I will actually find that it's 0.323 meters. And that again deserves a result, double underline, and an answer arrow, because that is really what was asked of us here. And that concludes our problem. We now found the stretch in the springs by applying the stretch formula, or really Hooke's law here, to the results from our free body diagram and our equilibrium. So we did not get confused by these springs here initially. In fact, we ignored them here. If you take a look at these equations and this free body diagram, we completely ignored the fact that there were springs, and we just then later on said that, hey, AB is actually connected to a spring, and so is AC, which is connected to another spring, and we were able to use that information to find the stretch in each springs. If these stretch are really practical is a different question. This is obviously very large, so 0.3 meters, that's 32 centimeters, that's almost like a foot. And if that would move a foot, that is probably not something practical in structural engineering, but it gets the educational point across. But I believe that completes our problem here, and we are now well prepared to move on and to solve any homework problem that includes springs. So now that we have a solid understanding of equilibrium in 2D and forces in springs, we can actually move to a little bit more complicated structures, and complicated is not really that complicated if we build it step by step. But let's look at this system here. We have a more complicated structure, in quotation marks, which has two weights hanging here and has the geometric configuration that is shown here. So let's read the problem statement and let's find out that we need to determine the tension in all cables if container F has a weight of 4 pounds and theta is 15 degrees. So let's put the information in here first. So this here would be 4 pounds and theta is equal to 15 degrees. And that is not a mistake. You may think like, how am I supposed to solve this? I'm short of one information here. And I would encourage you to pause the video right now and really try to solve this problem before I go ahead and show you how to do it. Because once I show you, you can never unsee it and you can never go through that learning experience ever again. This often seems like a problem that has not enough information for students because, again, the weight here for E is not given, but that is not a mistake, that is on design. So please try to work your way through it. And by working through it, I really mean work your way from node to node. So note that you have here AB, BC, and CD. And some of these nodes, with the information given, you can actually solve, whereas others you can. And I give you time to pause the video now before I move on. All right, I'm pretty sure you were able to solve it because you're fantastic mechanics students, right? So now I can explain to you how I would have done it. let's take a look at the individual nodes. And let's remember that if I release a node, I can always release every node from its system. So I have one here, I have another node here, and I have another node here, and I have another node here. So first of all, let's kind of forget about A and D, because if I solve any one of these, I already know what's going on in the rest. But just so you understand how A and D is working, please understand that there must be a force that is pulling up, and because you have a force that is not vertical here, right? So this AB member is not vertical, it's not acting in this direction. It is actually pulling to the left. Therefore, the support here on the top actually has to react to it, and we will talk much more about this in the future, but you have to pull in that direction. Likewise, on the other side, you have to pull up and to the left. But let's forget those two now. Now, I probably intuitively would cut either node B or node C, and that's probably what you did when you solved the problem yourself, but let's understand why it is only possible to solve node B first. You could write down the equations for node C and you can draw the free body diagram, and you will find that you cannot solve it. But why is that? That is because you have 1, 2, 3 unknown. And remember that we only looking at a 2D structure here, so we have the sum of the forces in X being equal to 0 and the sum of the forces in Y being equal to 0. So therefore you can only have 2 unknowns, right? 2 unknowns. And that is violated here in cut C or node C. Whereas in node B, you actually only would have unknown 1 and unknown 2, and unknown 3 is actually known because you know that there's 4 pounds pulling on it. So what you will do is you will first set up the equation for this node, and I will do that for you in a second, and then you take the information from here over to here, so that effectively this one unknown disappears, this one here. So now you actually have only 1, 2 unknown, and therefore you can also calculate the weight of this to keep it in equilibrium, the weight of this container at E. So rather than solving this problem for you, because you already did this anyways, but I'm going to show you that first I would do the free body diagram for node B. Then second, I would find equilibrium, so equilibrium equations. For node B. And that would really give me, if I solve this, so solve, this would give me FAB and FBC. So that in my third step, I can now apply force FBC to node C. And please understand that FBC is a tensile force, right? Is tensile force. And therefore must pull away from node C. So this can often be confusing because students think, hey, I calculated my force for node B and BC was pulling to the left. It's away from the node, therefore in tension. So if it's going to the left here, then up here in node C, it has to go to the left as well, is what they think. But that is incorrect because remember that we're talking about tension and we cut the system. So if I draw that in here, you will see that here I have tension because I cut there. And Of course, tension cannot change to compression just because you move to a different node. So up here at node C, there must also be tension. And now you may ask yourself, how is that possible? There are two arrows pointing towards each other. But keep in mind that you actually did a cut here and you did a cut here. And therefore, you actually have this middle part also in tension. And that really allows you to keep equilibrium throughout, and also makes sure that you have tension from here to here, from here to here, and from here to here. So please understand that you need to apply the force sometimes opposite depending on what force state you are dealing with here. But yeah, so my point to you is pull away from node C. So once you did that, you can now apply this force. And so in my fourth step, I can now draw the free body diagram. So fourth, which is free body diagram for node C. And then fifth step is to use equilibrium to solve for node C. And once you have that, you can really answer the entire problem where it says find all the cable forces in the system. And so I probably don't need to solve this for you here numerically. In fact, it is a good practice for you to do that yourself. But so you can check your answer, let me just tell you that if you solve this properly and you find the ultimate answer, which is the weight of the container at E, you will find that weight of container E is equal to 0.975 pounds. 0.975 pounds. And that is an answer here, so I guess I got to double underline it. And that is the answer you should arrive at if you solve this properly. And I really encourage you to do this and find a way to check your results. One way, for example, of checking your results is, let's write down the overall equation for this cut cloud. So let's say that you make this cut. For example, this is one way to look at it, which is effectively the entire system. So if you apply the 4 pounds down here, and then the 0.975, then you should find that the sum of your forces that are released here, which is going up, and here, which is going up, that those two forces, and maybe I should give them a different color. Let me do that. Let me make them orange here for you. So this plus this, of course, needs to be 4.975 pounds. That is the force that needs to pull up. So please double check your answer here and make sure that your force is pulling up with 4.97 pounds. This plus this must be equal to this. That is once again the sum of the forces in the x direction. But now you have all the tools that you need to solve this problem. I wish you good luck with that. And let's move on to our homework. All right, let's see what we took away from today's lecture. You definitely should have learned a lot of things about spring constants and springs, how they act in the structural system, but only you can really answer this. Also, the only thing that you can answer is what is the stuff that is not clear to you yet. So please go through that exercise and make sure that you come up with strategies that help you to really find more clarification about that. And let me know if I can help you with that. Last but not least, let's make sure that we understand our checkpoints here so that we can move successfully into our next lecture where we need this knowledge. So first of all, I definitely understand Hooke's law and I understand what a spring constant is and how that applies to the system. So I can definitely check that off. And because I understand this, I also understand the physical significance of a spring constant. That, for example, it takes, let's say, 100 Newton to stretch it 1 meter. That's the example we used. And you hopefully understand this and can check this off. And then you understand that the equilibrium conditions are really not different for spring problems. And you can calculate the forces in those spring cable structures, because it is just what we did in the last lecture with some add-on. So we understand that. And we can now, of course, use the stretch formula to determine the displacement or the stretch in a spring system. So today, very few checkpoints. They're all very closely related to each other. But it's important that we have a solid understanding of that. So that concludes our summary page and what we took away. So let's move on and talk about the homework. All right, I believe we are very well prepared for our upcoming homework now. So let's take a look at each of the individual problems for which we're dealing with 2D equilibrium, including springs. And for our very first problem, you are asked to find the forces in these cables in BC and BD under the assumption that the spring AB is stretched by 250 millimeters. And keep in mind that this is given in millimeters, where this here is given in kilonewton per meter. So this value comes from your variable sheet. So please understand that these units need to compare to each other, so you have to do some conversion there. But once you've done that, you can calculate how much force is acting here, and you can then analyze how much force is acting in these cables. So it's kind of the reverse of what we've done in the lecture, just to solidify your understanding of Hooke's law and equilibrium in 2D. That means we can now move on to probably the most fun problem in this whole lecture series, which is this funny contraption here on the bottom. Let's first read the problem statement before I give you some visual and geometric pointers for this problem. So in the picture, each spring is stretched by 300 millimeters. So assume that these are already stretched by 300 millimeters. Before the stretch, the distance, the separation between point C and C and A was actually 2 meters. So H used to be 2 meters when the springs were unstretched. Now, the cable that wraps around A, B, C, and D, that cable here, had a total length, or does have a total length, of 4 meters. And that cannot change. It's a self-contained loop, if you will. And now, before I read on, also notice that we have these containers here, for example, the one here on the bottom left, that wraps around the pulley and then attaches to point B, which really pulls the system to the left, whereas at D, it pulls to the right due to gravity acting on these containers. And so that means it wants to stretch this diamond-shaped thing out, and therefore the spring here goes down and this spring goes up. And the problem is really for you to determine the mass in kilograms of each block to keep this system in equilibrium, under the assumption that each spring is currently stretched 300 millimeters. And keep in mind that here you read millimeters and here meters, just like before. You, of course, have to make that unit pure. Now, let's talk about the geometry of the system. So again, this cable here wraps around and that stays 4 meters long, no matter what you do to it. Also, please understand that there's technically some symmetry to this system. So, for example, I could divide the system in two, and because it's symmetric, both containers, of course, have to have the same weight. So maybe I'm only going to care about one part of the system. For example, I can cut it like this, and I can only analyze whatever is going on in here. Don't get me wrong, if you make this cut that I drew with a solid line here, you will not come to a solution. It's not possible. But you can look at the individual nodes here, these ones, and you can, of course, calculate how much force the spring applies to this node. And be careful, because whatever this spring applies, of course, again, it's stretched, right? So it pulls up, and therefore that force is divided into this part and this part. But only this right side here really applies to this system. So I encourage you to think deeply about this. And once you understand what's going on at this node, you can move it down to this node, which then leads you to the weight in this container. And because the system is symmetric, this container is just the same as this container. I believe that should conclude the explanation for this problem. I wish you good luck with that. I'll be honest with you, it's not necessarily simple when you start with it, but I believe with the knowledge that we presented here in these lectures, you have all the tools you need to solve this. And if you have questions, of course, I'll be happy to help you through the discussion boards on Canvas. Good luck with that problem. It's a real fun one. All right, last but not least, we have a problem that is given in two versions in its original state. I call this the unstretched state, so it's a little bit more faint. And then you have the stretched state. So that is this portion here where you have the solidly drawn picture with the weight hanging on it. Let's read the problem statement real quick. Determine the mass in pounds of the cylinders, assuming that the sag S, so that's this value here, due to the cylinders is 0.5 feet. If the cylinders are removed, S is equal to 0. So this S would not exist. That's what this picture here is showing. Only if you hang the masses on there, you would actually create a vertical displacement. And yes, this is called S as well for sag, but please understand that this is different than the stretch of a spring. The stretch of the spring would be in line with the spring, and that is not what's asked of you here. We are looking for the vertical displacement. And that, of course, is different for each student depending on their variables or the variable combination of A and D. So please calculate that based on your individual numbers. But I believe that you can solve this with equilibrium and everything we talked about in this class. Notice again, it's a symmetric system. So here you have K2 and K2. So both sides have equal stiffness and we have equal distance. Also, please understand that this length here does not change. Look that these are not connected here. So A and B are always apart by 1 foot, and that does not change no matter how much you pull it down. So in other words, you have a vertical, perfectly vertical displacement here because this cable keeps the springs in the same distance as long as the cable is in tension. And I believe that prepares us well for homework 3B, for which you study the equilibrium of particles, of course in 2D still. Please make sure that you develop a solid understanding of these concepts, because in our upcoming lectures, we will take this to the next level and talk about 3D structures and 3D structures with springs in it. My experience is that students are sometimes a little bit afraid of 3D analyses, but my goal in the next lecture is to show you that this is actually nothing to be scared of. If you have a solid understanding of what we talked about here today, you are definitely ready to move on. And I will show you how simple it can be to take this to the next level. I'm excited about that, about the upcoming lectures, because we can use that to analyze real life structures that we see in our everyday lives. And therefore, it's always more fun to apply it and to learn more about how the real world works. Until then, I wish you good luck with solving your homework. Stay safe. I see you in the next lecture.